Question 3 is also a transition element question. So define the term transition element. I think I talked about it earlier when we cover question 2. So transition element forms ions or compounds with partially filled d orbitals. Okay, so you must have electrons in the d orbitals, but it must be partially filled. It cannot be zero. It cannot be fully filled. Now state how the melting point and density compare with your calcium. There are two things. The melting point of transition metal is a lot higher. So the melting point of iron is a lot higher than calcium. So this is just stating, they're not asking you to explain. The transition metals melt and boil at a higher temperature. Transition metal also has a higher density. So density of iron is higher than calcium. So I am just stating, I am not explaining. B part 1. So this question is actually about not really about transition metal, it's actually about electrochemistry. They want us to define standard cell potential. So there are two bits to this definition. First of all, you need to know what the standard conditions are. So standard there refer to standard conditions, which is 298 Kelvin, 1 atm pressure, and of course in the context of electrochemistry we're also talking about 1.00 mole per dm cube. And then we're talking about cell potential, we're not talking about electrode potential, so be very careful there. I've always remember my definition of standard cell potential as a measure of the tendency of electrons to flow through external circuit. If you don't like this definition, you should go for the other one, which is to do with the maximum. So this is in fact probably much better. So the maximum potential difference, the moment you see this term called potential difference, is to do with two electrode system. So it's between the electrodes under standard conditions. So this second one is probably a lot more complete compared to this first one. So I can write down my standard conditions straight away. 1 atm pressure as well as 1.00 mole per dm cube concentration. Okay. I guess what I can do then is probably just put this into a square bracket, not a square bracket, a square box there, so that you can probably think about it with regards to what is being asked there. The next part is not surprisingly, they do want to give you some free marks. So they give you the opportunity to actually get some free marks here and there. You're expected to draw a fully labeled diagram for 3 marks. So if I just label my apparatus, nope, I don't want a curve, I want a bigger container, another container. I will have a high resistance voltmeter, and I'll have a salt bridge connecting these two together. I have a metal ion and a metal, so I would need a metal electrode there. I have a metal ion and a metal ion, so I need another metal electrode there. But here I need an inert electrode, which is platinum electrode. But on the other side, I would need a copper electrode because I have a metal and a metal case study. A metal and a metal ion, a metal and metal ion means I need 1.00 mole per dm cube Cu2 plus aqueous, which could be from copper to sulfate if you want to. And then this is a metal ion and metal ion, so I have 1.00 mole per dm cube ion 2 plus aqueous, and also 1.00 mole per dm cube ion 3 plus aqueous, and this is equimolar after all. Okay, so this is a metal ion and metal ion case study, so I need a platinum electrode. This is a metal ion and a metal case study, so I need the metal as the electrode itself. I haven't completed the circuit until I label the salt bridge there, and I also need to label this as high resistance voltmeter. So the idea of high resistance is so that they will allow you to measure the potential, the maximum potential difference, which was actually the definition for E cell. include all necessary reactants. I did that. I should probably just mention this is at 1 atm pressure, 298 Kelvin or 25 degrees Celsius on the side there. Question 3, part C. So this looks like, this is actually part of catalysis. This is homogeneous catalysis. It comes under the last bit of the A2 rate of reaction topic. So they say use equations. If you read the questions, they say equations, there's plural, because this is catalysis. So you need to show the catalytic role of Fe3+. So if you think about it, the overall reaction is actually S2O8 minus plus I minus going to I2 and SO4 minus. This is not thiosulfate, this is peroxyl disulfate. It's a case study in A2 rate of reaction as part of the essay on homogeneous catalysis. So there's 2 of that, and there's 2 of the iodide as well. So overall, you can hopefully see that there's 2 minus and 2 minus. So you get 4 minus there, 2 iodines, 2 times sulfur, 2 sulfur, 2 times 4 oxygen, 8 oxygen. This is the overall reaction. I hope you can appreciate the idea is that this is a 2 minus and this is a minus. Negative charges repel. So negative ions repel each other. So that means if you want them to react, they have to collide with each other. That's going to give you high activation energy, slow reaction. So what is going to be your catalysis? Your catalysis involves reacting with iron. When you think about this, the iodine there is iodine -1, the iodine there is iodine 0. So that is an increase in oxidation number. So this is oxidation. My catalyst here, they say add a few drops of iron 3+. So iron 3+ doesn't want to go to higher oxidation state. So the iron 3+ will go to iron 2+. If the iron 3+ go to iron 2+, this is a decrease in oxidation number. This is reduction. If you want to do reduction of this, you need to find an oxidation partner. This is the one that get oxidized. This is the one that get reduced. So I start with the one that get oxidized first. So Fe3+ plus 2I minus going to I2. And of course then I need 2 Fe3+ and 2 Fe2+, because, well, to balance out the changes in oxidation number, of course, and also to balance out the atoms. So this is 2 times plus 3 is plus 6, minus 2 is plus 4, 2 times plus 2 is plus 4. Positive ion and negative ions, at least no more repulsion, much lower EA, alternative reaction pathway, much faster reaction. This is one equation. This is showing that Fe2+ is converted to Fe2+, but you haven't shown that Fe3+ is a catalyst yet. So what happened is the Fe2+ will react further with S2O8 minus. If you look at our original equation there, that will give you the Fe3+ again, and they will give you the 2SO4 minus. Again, you need to balance the changes in oxidation number as per AS redox reaction. In the topic, they say use changes in oxidation number to balance chemical equation. So now this is oxidation, which means this is the reduction, which is the accompanying partner. Plus 2 times 4 is plus 4, minus 2 is plus, what am I doing? Plus 4, minus 2 is plus 2, plus 6, and then 2 times minus 2 is minus 4. So overall you get plus 2 on the right as well. So now you can hopefully see that Fe3+ is regenerated. And in doing so, now you have a plus charge with a negative charge. Again, this one will have much lower activation energy than the 2 negatively charged ions coming together. 2 equations, so 1 equation and 2 equations. They are not looking for this equation. This is just overall. It doesn't show the catalyst in there at all, because a catalyst is never used up in the reaction. They just simply get involved in the reaction. This is your intermediate, and then your intermediate further reacts to regenerate your catalyst. C part 2. So this is question 3 actually. So we have Fe3+ can oxidize I minus, and then that blah 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 cannot oxidize I minus. I think we need to appreciate the idea of I2 plus 2 electrons going to 2I minus. We need to look at the E note from the data booklet, which I am just opening right now. So I2 going to I minus is plus 0.54 volt. Everything in the data booklet shows reduction potential. Next up, I need to look at Fe3 plus aqueous. So they are in alphabetical order. Fe3 plus going to Fe3 plus plus 3 electrons. Going to Fe is minus 0.44 volt. Should probably ignore that E not there. And then I also have another Fe3 plus going to 2 electrons, which is the one above it. Oh no, sorry. The one below it is actually Fe3 plus electron going to Fe2 plus, that is plus 0.77 volt. Which other one am I looking at? Something that has got Fe3 plus in it. Okay, so the other one is FeCN6, 3 minus, plus electrons going to FeCN6, 4 minus, and this is plus 0.36 volt. So we look at what happened there. So they say that I minus is your reactant. They say I minus is your reactant. So this is your reactant. So we are going this way, which means this is our EOX because we are trying to lose electrons. This is the EOX, which means we need to find ERAT. If this is your EOX, and we know, so we gotta use E naught values to explain these observations. In terms of all this, your ERAT has to be more positive than your EOX. This is iron 3 plus. If you want the iron 3 plus to oxidize this, the iron 3 plus itself has to be reduced. The iron 3 plus itself has to gain electron. So this is going to be more positive. It should be more positive than the EOX, but this is less positive than EOX. So it's not going to go to iron. Okay, so this is not what we are looking for. I can cross this out. They say use E naught values to explain the thing. So I should really, list down all these things as part of my explanations, because although these are from data booklet, you really need to list it down in your answer in order to explain it. Okay, so how can I explain it then? Between this and this. So this being the ERAT, because I'm doing the reduction as I'm going this way. So that is reduction. So those are going to be my ERAT and ERAT. So for oxidizing I minus with Fe3 plus, the E cell is equal to ERAT minus EOX. So the ERAT is going to be more positive than that. So plus 0.77 minus plus 0.54, and you can see that there is going to be a positive number. I'm just going to press into my calculator. I get plus 0.23. Your calculator actually doesn't show you the plus, but you must have sign value and units for this kind of question. Therefore, feasible and spontaneous. As you know, when the E cell is greater than 0, the reaction will be feasible and spontaneous. On the other hand, with FeCN6, 3 minus, the E cell, again, our ERAT there is going to be that. If we want to use these to oxidize the I minus, that means this one get reduced and this one gain electrons. So if that is your ERAT, plus 0.36 minus your EOX, which is still the same, oxidizing the I minus going to I2, plus 0.54. So this is a hypothetical situation, and we are just using our E naught value to work out whether it's possible or not. Here, this is minus 0.18 volt. So this is lesser than 0. So this is lesser than 0. Therefore, not feasible and not spontaneous. Not going to happen under room temperature and condition. So that's the whole idea of using E naught in order to do this kind of question. Using E naught, explaining whether it's feasible or not. Alright, so for that 2 marks, should be able to write out or state these equations with the correct E naught values and do a bit of simple calculations for E cell to work out whether feasible or not feasible. Question 3, part D. This is related to the previous question. So here, instead of iodide, you have the tartrate. So tartrate looks pretty much like the iodide in the context that, still minus 1 charge. So it is still something which is negatively charged. If I just write that down. So, well, actually it's minus 2 charge. It's a dicarboxylate, like that. if you draw the skeletal formula a bit better, it should be written like this. Okay, so this is just a more complete skeletal. This is what is given. So why is it still slow? Slow without catalyst. Slow without iron 3 plus catalyst. It was the same reason as I mentioned just now. High activation energy, high EA, because above the reacting particles, in this case they are ions, above negatively charged, therefore repel each other. So very slow reaction there. And in part 2, so we gotta use the overall equation. I guess the fact that they say use the overall equation to deduce, so we can think about the overall equation being the redox equation, where we have the oxidation plus the reduction half equation. So I can immediately see the S2O8 2 minus going to SO4 2 minus. This is a bit tricky because as far as, oh yeah, okay, I think I get it now. So there's usually 2 times that, because 2 times sulfur give me 2 sulfur, 4 times 2 give me 8 of that. And you can imagine balancing the charges. There is 2 minus times 1 is minus 2, 2 times minus 2 is minus 4. So this is going to be a reduction. You need 2 electrons on the left hand side. So minus 2 give me minus 4. So minus 2 times 2 is minus 4. So this is one of your balance equation. This is a balance half equation for reduction, because you are gaining electrons. So gain of electrons is reduction. So reduction is gain of electron there. What you could see very obviously is that this is 6 in the equation. So meaning to say they multiply that by 3 such that you get that. So obviously you don't write all of this down in the actual exam, but this is the way you're thinking in your head, that you have the whole thing multiplied by 3. You're looking at something with 6 electrons. So there's something that you have to include in your half equation for that question part 2, because changes in oxidation number is in terms of the electrons. If you have 6 electrons as a result of this equation, you must have lost 6 electrons from the ethane, not the ethane, but the tartrate ion there. So if I write C4H6O6 2 minus plus something, that will definitely give me 6 electrons, because I'll have 6 electrons on the right. Looking at the overall equation, if you cut out the 3S2O8 2 minus, if you cut out the SO4 2 minus, what we are left with is just whatever on the left. So the 1 of the tartrate plus 2 of the water, I will get, what do I get actually? I get 2 CO2, I get 2 HCO2 minus, I get the 6H plus as well as the 6 electrons. 6H plus and 6 electrons. The 6 electrons is what I add in, because these are not included in the original overall equation. I'm just simply taking out the 3S2O8 2 minus and the 6SO4 2 minus from the equation, such that this is whatever is left on the left, this is whatever is left on the right. I know 6 electron there, because if I know these half equations, then I know I need to have 6 electrons if I multiply the whole thing by 3 there. Okay, or of course you could balance everything, and then in terms of charges, minus 2 times 1 is minus 2, no charge, overall is minus 2 on the left, 2 times minus 1 is minus 2, 6 times plus 1 is plus 6, so this gives you plus 4 to go to minus 2, so plus 4 to go to minus 2, you need to gain 6, you need to have 6 electrons on this side, meaning to say you're doing oxidation, which is loss of electrons. That's how you can balance this equation very, very quickly as well. To the next part of this question, E part 1. So this is a lot more organic reactions. We got to complete this table. They want the organic product. They have simply said structure. They don't mention display, structural or skeletal. They just say structure. So I personally would draw skeletal, because that is my favorite. I don't know what your favorite is, but this favorite of mine is fast, it's elegant, it's easy once you know what is going on, and it's something that you have to get used to if you want to do an exam. Master your skeletal formula. Okay. So the first reaction there is excess of lithium aluminium hydride this is a reducing agent, so it's a source of H minus. It's a reducing agent, so it will reduce your carboxylic acid all the way to your primary alcohol. So I will get alcohol all over from the original carboxylic acid, but I need to be careful. I have done something wrong here. I've gotten 2 carbon, whereas I should have 4 carbon to begin with. You see, when you draw skeletal formula, you need to be very careful about what you're drawing. Otherwise, you might lose the carbon. So let me just draw that again. Carbon, oxygen, and then OH there. So this one is going to be 1, 2, 3, and 4. There are 4 carbons, just like there are 4 carbon in tartaric acid. If I draw out tartaric acid, that was the tartaric acid that is given in the question. So we're talking about this particular carboxylic acid and this particular carboxylic acid. They get reduced all the way to the primary alcohol there. This type of reaction is called reduction. On to the next one, you have an excess of CH3COCl. This is what you call acyl chloride. That is the class of there's a functional group in reality. The name itself is called ethanol chloride because there are 2 carbon acyl chloride, just like that, 1 carbon, 2 carbon. Acyl chloride is a reactive version of a carboxylic acid, such that you don't need a corn sulfuric acid as a catalyst in order to form ester. So this behaves like a carboxylic acid, meaning to say your alcohol will be untouched. So your alcohol is untouched. Oh, actually, no, your alcohol, it will be the one that reacts. What am I talking about? So your carboxylic acid will be untouched, like that, but your alcohol will react, and they will have 2 carbon ester like that. They will have 2 carbon ester like that. So you can hopefully see that, you know, this thing there come from the ethanol chloride. This thing there come from the ethanol chloride. There's the one that behave like carboxylic acid. They will form ester with your alcohol. They'll form ester with your alcohol. You use excess of it, so you can never stop at single ester being formed. This reaction has a name called esterification, but they are specifically looking for type. A lot of students are confused between type versus name. In your AS introductory organic chemistry, there's a list of the type of reaction. None of them contain esterification. That's because esterification is the specific name for the reaction, whereas the type is going to be condensation. When you form an ester, it's called a condensation reaction. You have learned this in IGCSE or O-level chemistry as part of condensation polymerization, and you have learned it in AS, and you learn it again in A2 as part of condensation polymerization when you form polyester or polyamide. On to part 2. So what we have then is, this is the last bit of this question. This is E part 2. So tartaric acid reacts with amine. So if I just redraw tartaric acid, because a lot of this type of question is a lot easier if you have the structure in front of you. So this is tartaric acid, and they will react with phenyl, 1-phenyl ethyl amine. So I have a phenyl, which is C6H5, and then CH, and then NH2, and then CH3. This is actually oh wait, I was going to say amino acid, but this is not amino acid. And they said that they will form an ionic salt. So show the structure of the salt. This is an amine. So an amine is a base because it's got a lone pair on the nitrogen to accept proton. So it's a proton acceptor. Which one is going to donate you a proton? Well, you have 2 groups that can donate protons. This is your carboxylic acid. Your carboxylic acid is pH lesser than 7 because that is an acidic group. Same thing there. There's another carboxylic acid group. So when you have they say an ionic salt, okay? So the key thing here really is the question say an ionic salt. And then they say draw the structure of the salt. So in accordance to what the question is saying, there's only one salt that you're forming. I will be tempted to say that, both of them will get deprotonated rather than an option for one of them getting deprotonated. So there's all minus like that. and there's O minus like that. And what I'll have is I'll have the phenyl ring, and then I have the methyl group, or I can have NH3 plus like that, and then the methyl group, and then I can draw another one. So my phenyl or my benzene ring is not drawn very well. Gotta improve on my drawing of that. I had drawing that 6-member ring actually. Okay, that's as best as I could do. Hang on, it's bonded to carbon, and that carbon has got NH2, which is now protonated. Now it's NH3 plus. I have an O minus and O minus, so I have one of these there and one of these there. So make sure that you are not forming covalent bond between this and the nitrogen, because the nitrogen is a second period element. They cannot form more than 4 covalent bond there. So this is going to be the structure of the salt that you are forming there. Don't know if I can draw it in a box. Would it be better? I don't think so. Yep, it looks better there. So the structure of the salt form is a dianion, so you get dication as a result of that. Lone pair acceptic H plus, so you need 2 of them because both of them get deprotonated. They want the salt. That's the end of that 17 mark question number 3.